who's going to tell us about testing gravity with LSST.
Hello, yes. All right, can you hear me? Yes, you can. Good. So I want to thank again the organizers for the invitation and for the great idea of putting the workshop together. And what I want to talk about today is some work that we've been doing on testing more than gravity. It's like testing what can we say about different screening mechanisms from the side of the simulations analysis, right? With the idea of LSST coming up soon. So this is work that we've been doing with the shared collaboration, which is an acronym that, of course, comes from something that is put together in some way, which is Santiago, Harvard, Edinburgh, and Durham. So, and this is sort of done with lots of support and with some idea of participating with in the planning of LSST with DESC. So the things that I want to go through today are a little bit of what are these modified gravity models. That's models without cosmological constant that luckily Tessa yesterday gave a great presentation about. So I'll be able to go very fast and not go into the details, which I don't know. So that would be great. And then I will talk a little bit about the simulations that we've been doing, and in particular of making emphasis on what is the aim, what we want to do with these simulations, right? We want them to have different gravities, but we want them to have the same galaxy clustering, because that's something that we can measure, so that's something that we have to satisfy. And what can we do once we have these simulations to see differences between the different gravity models? And we'll see that this leads to possibilities of differentiating between screening mechanisms that can be present in there. So we've seen several slides like this one today. Oh, sorry, during the conference. We have a very successful model under color matter, which 70% is in this dark energy part, about 25% is in the dark matter part, and there's a little bit of variance in there. And these two things are actually quite interesting. There are ideas of what these different things can be. Perhaps, of course, this is taking into account general relativity. The thing is that this 70% that's associated to dark energy is perhaps the most problematic one, right? Dark matter has several different candidates from particle physics that are quite compelling, so maybe that's the answer, maybe not, we don't know, right? But the idea is to modify gravity so that we don't have to use this dark energy sector here, right? So that's what people have been thinking about. This is a slide similar to the one that Tessa showed yesterday, but this one is made by Bajul Lee, of the different degrees of freedoms that people can use to modify gravity in order for it to not have dark energy. And as you saw yesterday, there are several different options, many of which can be put within this Horndeski model parameterization that Tessa was talking about. In particular, the ones that I'm going to show you results about today are F of R and brain world models. In particular, the normal, the Valli, Cavallazzi, and Porrati model. And I was talking to Tessa this morning, and apparently both can be put within the Horndeski framework once you are within the horizon, roughly, right? And a low redshift. So what do these different models do? What is the objective of having these different models? Well, what you want is, of course, you don't want a cosmological constant or dark energy, I guess. And it's possible to think about these modifications as a scalar field which is coupled to matter, right? Even if you also put some extra terms in the Einstein-Hilbert action, you can sort of think of it like that, at least in these two different models that are put in here. And what this modification does is add an extra force, which is called the fifth force, right? In the case of F of R, it doesn't really add an extra force. It's just that the fifth force is sort of like the difference between the standard cold dark matter with cosmological constant model and the F of R model. In the case of the DGP model, the brain world model, it depends, right? So the important thing is that the screening mechanism, the way in which this fifth force is suppressed in high density regions in order to make the theory compatible with observations, in particular observations of CMB and solar system, which are high density regions, right? The way in which this screening mechanism comes into play is different, right? So in principle, we know that if the CMB is the same and solar system should also be satisfied with these theories, the place where you want to look for differences between these theories are empty regions of space, right? And we'll see what that means, right? That could be voids, or it could also be the areas that surround halos in general. So, good. CMB, you don't need to simulate this. This is linear theory. You still need numerical solvers for this, but you can get away with just doing the linear approximation to actually put together your equations that you need to solve, right, to explain this. Instead, in the low redshift universe, what we have is galaxies. And galaxies have these structures that are extremely nonlinear. You have density contrasts of the thousands. So it is definitely completely nonlinear, and not only that, it's only populated by galaxies. So, people have been saying how galaxies populate dark matter halos, but it's always been done assuming general relativity. So, if we want to be perfectly honest, we sort of have an idea of how galaxies are distributed in the density field of matter. We just don't know exactly how. It's shocking, right? But it's like it is. So you can think of it like that, but you can also think about it as if, we still have some freedom. We can still do something about this, right? We can play with this a little bit. And that's what we want to do. So a little bit of details on the models, in particular so that we know how people simulate this type of gravities, okay? So in the case of FOFR, you have this modification to the action that Tessa told us about yesterday, which is basically the general relativity action that has just a Ricci scalar there, plus a function. That function needs to be sort of tailored so that there's a screening mechanism built in within it, okay? And in this case, there are some regimes where things behave differently, right? So if you have high curvature or high density, then what happens is that f of r approaches a constant and behaves like a cosmological constant. And in the other regimes, it gets really complicated and interesting, right? Things could happen that we can actually go and see what they are, right? So this is the general equation that comes from varying the action. There are a couple of limits so that you can actually identify which of the parameters of this function should actually be put in to mimic the exact same expansion history that we have for lambda CDM, okay? And right, when the derivative of this function as a function of a Ricci scalar goes to 0, it's basically when also the density goes up. So that's the case where you don't have any effects from this extra term, okay? In particular, there is one function for f of r, that's a Huan-Sawicki function that satisfies a condition, okay? So that's basically what we're going to use. Right, so once you go into the regime that we can actually sort of take into account to model the distribution of fluctuations within the horizon in some sort of way that we do with simulations, which are slowly varying density contrasts, and in particular, when you can have a negligible kinetic energy for the field, you have this modified Poisson equation that has this term that's related to the derivative of f of r with respect to the Ricci scalar, and this equation to solve that particular field according to what is the density field in the universe. So the two things are coupled, right? So you need to solve these two things together to find out what the gravitational potential is. And in particular, this is the Huan-Sawicki f of r function, which we have here. It has these three parameters. These two parameters in particular can be related directly to to the lambda CDM parameters, omega mater and omega lambda. And there are these two extra parameters, n and FR0. N is set to 1, usually. And FR0 is basically giving you what is the amplitude of this function. So, and it's also related to the derivative today of f of r function as function of the, sorry, with respect to the Ricci scalar. So if you make this parameter very, very small, it just approaches a lot general relativity, right? So current constraints on, for example, cluster abundance tell you that this parameter FR0 should be smaller than 10 to the minus 4. There are actually more tighter constraints that actually take this quantity down to 10 to the minus 5. So that's the limit that we are going to adopt in all the results that I'm going to show you. So very good, right? So this is our small modifications that are very subtle, right? So that we want to see what happens in this case. And this FR0 is going to be called the chameleon parameter, right? The larger this parameter is, then the less screening you will have in your theory, right? The more different it is going to be from general relativity, and it's always going to be different powers of 10. 10 to the minus 5, 10 to the minus 6, and so on, right? So one thing that you can do to try to guess what happens in the nonlinear regime with these theories is to just do a spherical solution with a spherical top hat density distribution. And in this case, for example, if you think of a halo as a spherical region with a constant density inside and the constant density outside, what you find is that the Newtonian force of gravity points toward the halo, which is reasonable, and the fifth force also points toward the halo. So halos will tend to grow a little bit more in f of r than in gr, okay? And, the high masses, depending on how strong the fifth force is, depending on this FR0 parameter, you will have more or less differences. And it changes. It doesn't affect all masses in the same way, but that's something that we can actually see with simulations, not with this simple model, right? And the other regime where you can look at what happens with the fifth force is the so-called void regions, okay? So let's make a little bit pause here to define what is void to astronomers, right? So astronomers use the distribution of galaxies to find the void. So we don't really know if voids are of matter, right? We only know that, for example, in the most extreme case, a void will have no galaxies, okay? But, maybe you're using galaxies of 10 to the 10 solar masses to find your voids, and you'll have plenty of small dwarfs inside the voids, right? So, and it's even worse than that. People even allow galaxies to be inside voids of the galaxies that they're using to select the voids. So voids are mere underdense regions in the density field of whatever, right? For sure, in the mass density field. So there's always going to be some mass within the region that you consider a void. So the density inside the void is different than 0, okay? So it's again the spherical top hat model. In this case, the density inside the sphere is just lower than the density outside the sphere. So this is a void, right? And this case, Clampett 2013, they actually did, collaborators, right? They did the solution for the first time. They proposed what the equation should be, found the solution by parts. And what they find is that, yes, since you have some matter inside, there is a Newtonian force pointing toward the center. And the ratio between the fifth force and the Newtonian force is actually negative here. This is that ratio is a function of distance from the center of this distribution of matter. So the fifth force points outwards, which is contrary to what happens in halos. And this is really nice because one thinks, okay, so we will have more massive halos, but we will have emptier voids if we do this, right? Okay, excellent. So what about the other model that we're going to look at? So the other model is also a modified gravity model, but it is a normal branch of this 5D DGP model, okay? And what that means is that this model also needs a cosmological constant in order to produce the accelerated expansion of the universe, right? But the interesting thing is that there is a fifth force, and this fifth force has a different screening mechanism compared to what happens with f of r, right? So in this case, so the action has two components, one for the 5D for the book and one for the 4D space that we live in, the brain. And the mechanism that we have here is called the Weinstein screening mechanism that was initially proposed for something and then dropped, and then it was found out it could be used for this later on. So it is also a model with accelerated expansion. It wouldn't be needed in the SDGP model, which is a self-accelerating DGP model, but it's difficult to, it's probably a little bit unstable, so people don't really use it. But, right, and the gravity felt by massive particles includes this fifth force, which is also mediated by a scalar field. The extra parameter in this case is this crossover scale where the gravitons sort of pass to the bulk, which is a very large scale. It's a very, of the size of a survey, basically, right? So, in this case, the modified Poisson equation depends on this beta function that depends on the scale factor, and this beta function is the one that depends on the crossover scale here. That can be expressed in terms of the lambda CDM parameters as well. So when people do the spherical solution for the NDGP model, what they find is that around overdensities, there is a region where the fifth force is suppressed. So it is different from what you get in F of R, right? And that radius is called the Weinstein screening radius, which depends on beta and on the other cosmological parameters. So if we want to have the same cartoon picture of what happens in in halos and voids in this different theory, in this NDGP model, what we see is that we will have the halo with some density inside and outside. There's going to be a Weinstein radius that depends on the mass and, of course, on the crossover scale as well. This parameter, you will have a Newtonian force outside this halo. You will have a fifth force outside the halo, but within the Weinstein radius, the fifth force is 0, close to 0, right? So there's a fifth force outside the Weinstein region, which is in addition to the Newtonian force. It's slightly different. The phenomenology should be different in this case. And stopped working on this. Okay. So if we go back then to the example of the void with some inside density that's different than 0, there's going to be a negative force that's also going to oppose a Newtonian force, except that if you have a halo, which is perfectly possible, we said that voids actually do have galaxies and therefore also have halos within them, then that halo is also going to be surrounded by a Weinstein radius inside which the fifth force is going to be 0. So what one expects to find in a void is not the same for F of R than for NDGP, or if we want to say it more generally, it's not the same for chameleon type screening compared to Weinstein type screening, okay? So, and the idea behind all this work that we've been doing is to actually look at the different screening mechanisms, right? So, right, yeah, they're different, good. So, if we want to look at this, rather than, particularly for the NDGP model, which has this complication, right, this extra complication, if we want to do things like that we can know that we expect to find in the actual galaxy catalogs that we have, we need fully nonlinear solutions for these different screening types. And we need them to have the same galaxy clustering. And that sounds like a bit of a challenge, okay? So, perfect. So we have the modified Poisson equations for F of R, right? In particular for FR, for the field that depend on density, and then for the Poisson equation that depends on this field in particular. That can be simulated if you take advantage of, for example, of some codes that are made to do hydro simulations. So what Zhao, Li, and Koyama did in 2012 is used the ECOSMOC code from Baju Li, which is based on the Ramses code. And this way, not only can they simulate F of R, right, the chameleon type screening, they can also simulate the Weinstein type screening with this. So then what we did with the collaboration was to run simulations, in particular of GR and F of R, that start from the same initial conditions. So this is basically saying, yeah, both are perfectly compatible with the CMB, okay? So when you do that, you can do this with different box sizes. In particular, what we did is use this set of simulations that we have here. There are 1 gigaparsec and 1.5 gigaparsecs aside. There are different numbers of realizations so that we can calculate errors and do more covariance matrices and so on. And they all have the same initial conditions, so the structures are the same. All the difference that we find are going to come only from the different types of screening and not from the different structures that we see in the simulations, which is nice, okay? So this is an example. This is the GR output. And this is the output of f of r with FR0 of 10 to the minus 4, 10 to the minus 5, and 10 to the minus 6. The number after the f is just the exponent, right? So that you remember what they refer to later on. And, well, okay, at this level of detail, they'll look the same, right? You have this cluster is always there, and so on. But if we look at this a little bit closer, and concentrate on certain areas. For example, I think it's good if you look at this pair of halos in the GR simulation. When you move to the F4, to the most extreme model in F of R, you see that those structures have actually merged and formed, a single halo there, okay? And maybe you can also see this in GR. There's a little bit like a violet hue inside that void, right? And when you move to f of r, it sort of gets darker. But maybe I'm trying to induce you to see that. But actually, voids are emptier, at least of mass. This plot here is just showing particles, okay? So it's not galaxies. Good. So just to recap, what we said was that the halo should have an extra fifth force pointing towards it. So the mass functions are actually different as well. And this is simply showing the relative difference in the mass function of a simulation with respect to, of an f of r simulation with respect to GR as a function of halo mass, right? There are different panels here. This one is for redshift 1, this one is for redshift 0, and the top column is for when the screening is almost not present, so this is the largest difference with respect to GR, and this is the model that has the smallest difference. This is F6, this is F4. And what you can see is that you can have about a 30% difference at redshift 1, a little bit less at redshift 0, in the abundance of halos, which is basically showing you that, yes, in f of r, you actually have this fifth force that's making your halos to grow more. So the mass function is just moving a little bit to the right. So you have a larger amplitude of the abundance of halos in that simulation, okay? And as you move to larger screening cases that are closer and closer to GR, the differences, in the case of the full simulations, you have to look only at the black symbols here, right? The difference becomes only important, about 20%, at sort of like low masses. So it's really difficult to detect, right? But still, you have a larger abundance of halos in f of r, even in the case that is closest to GR. So a very tiny value of FR0 still makes an impact on your simulation here, okay? There's an enhancement at different levels of, at different masses of the mass function of your simulation. Oh, okay, fair enough. So one of the reasons why this model is ruled out is because it, for example, this model in particular, the one with no screening, FR0 of 10 to the minus 4, is because you have a factor of 2 more clusters of 10 to the 15 solar masses that are clearly incompatible with what people see, okay? And not only that, when you look at the power spectrum of the distribution of mass in these different simulations, and you again plot the relative difference with respect to GR of the different simulations, this is the green is the closest to GR, and the blue is the most distant one. You can see that there are very important differences in the amplitude of the clustering. So this is at redshift 1, this is at redshift 0, so it's stronger differences at redshift 0. And this is basically due to the fifth force making your structures grow larger, so making your overdensities become more extreme, right? So the power spectrum grows because of this. And, well, that is basically telling us that the clustering of mass is different, and even worse, sigma 8 is higher in these F of R simulations. But this is sigma 8 measured directly from the mass power spectrum. Okay? Good. So what happens with the other models that we're trying to simulate? So this is the case of the full simulation of the Einstein screening case. And again, in this case, we also have different mass functions. This is the relative difference in mass functions as a function of mass. You can see that, again, we have an overabundance of massive halos for this particular model. Just look at the purple line here. Yes, they're all roughly the same, but the purple line is like the full NDGP. So you have a larger abundance, but a few percent of massive halos. And the power spectrum, the relative difference of the power spectrum with respect to GR, is also different in the linear regime by about 20%, roughly 15-20%. So it also has a different sigma 8 for the power spectrum of the mass. Okay? But we said that, fortunately, we don't really know exactly how galaxies populate dark matter halos, right? So we can actually use this to try and see if we can get the galaxy population in all these different models with different power spectra, with different mass functions, different bias functions as a function of mass, to actually give you exactly the same clustering. And in particular, the clustering that we observe, for example, for the CMAS sample, okay, in Sloan. So to do this, we use the halo occupation model, right? Because of merging, as halos evolve in time, they merge with other halos to make larger halos. And what happens in the end is like a halo of a mass of a cluster of galaxies will have had, hundreds or thousands of mergers in its history. So they will have, that number of satellites within them, of halos, right? But not necessarily all of those halos will have galaxies, but some of them will. And if they do have galaxies, then you will see those galaxies are basically on the peaks of the density of those individual halos, right? So even though the halos merge, the peaks survive for some time, and in those peaks are the galaxies. So that's why we have satellites. We have Milky Way satellites. We have thousands of galaxies in a coma cluster, for example, and so on. And that happens because of the history of merging, right? So what one can see is that in the end, for a halo of a given mass, you will have a certain number of galaxies, right? So this is what this plot on the right is showing. It's showing the mass of the halo on the x-axis and the number of galaxies on the y-axis. And depending on the sample of galaxies that you choose, right, it's not going to be the same if you choose galaxies of 10 to the 8 solar masses. That will show you thousands of dwarfs in halos of 10 to the 14 solar masses, for example. Or if you choose 10 to the 13 solar mass galaxies, like the CMAS ones, okay? The result of the number of galaxies per halo depends a lot on your selection of galaxies. So, in particular here, we're showing something that is close to what one finds for the main galaxy sample of Sloan. You find that you have about one galaxy in halos of roughly 10 to the 12, and that this number increases as you go to higher masses, and it basically increases proportional to the mass, very roughly, okay? Excellent. And then there are a few parameters that actually allow you to obtain this shape. There's a function for how many central galaxies you will have in a halo, and there's another function for the number of satellites that you will have in a given halo, right? So the central is simply the dominant galaxy in your halo, the galaxy that sits in the center of potential of the halo. And what one can do is then take all those parameters that one has in this function and vary them in sort of in a way so that, for example, you give different weights to halos of different masses that have different bias factors. So with this, you can actually change the amplitude of the correlation function, and you can get rid of that difference in sigma 8 that we had at the beginning, okay? So that's what we did. This is what we did in the first paper by Maurice Kautun that came out this year. And what basically did is just find the halo occupation model parameters that actually allow us to fit the clustering of Sloan galaxies. So here on the right, we have, it's not only the galaxy clustering, right? We also want to fit the galaxy abundance, because we have mass functions, stellar mass functions for this galaxy. So we need the integral of those mass functions to coincide with the number density of the galaxies that we have. So this is consistent with what we see, right? So we can actually measure in clustering today, right? Before weak lensing tomography. So we can do this, we can still do this, right? So what we do when we fit these parameters is basically be able to match the correlation functions from 2 megaparsecs and onwards for larger separations to roughly 5% level. So the difference in sigma 8 of about 30, 50, 25% that we have in the simulations, when you look at the paraspectrum of the mass, go away in the case that you have these galaxy populations in those simulations for all the different gravity models. In this case, I'm just showing GR and two different models of F of R. Okay? But we can actually do this for both types of simulations, right? So yeah, okay, the freedom is there. People are, well, we're trying to also implement gas and stellar components. It's a little bit difficult to do this with galaxies because stars can be, stars maybe are not screened, whereas gas could be screened, and so on. So it's a bit complicated to actually do the proper dynamics of galaxies, and that influences how galaxies evolve in a halo. So it's not a simple problem to do this in a full hydro case, right? So we have this solution now. The actual HODs, the number of galaxies, on average, the average number of galaxies is a function of mass. As you can see, differ a little. Much difference, maybe 5% difference in number of satellites, but the differences in the tails at low masses are actually the ones that change the amplitude of clustering. So if you change a little bit the mass, the average mass of your sample, then the bias is different between your two different samples, and those bias factors basically compensate for the difference in sigma 8 in this case. Good. So we now have GRF of R and also NDGP simulations with the same CMB initial conditions, same structures, and we also have GRF of R and NDGP models with the same galaxy clustering and density. Good. So, okay, what difference could there remain after we do this? Well, maybe low density regions are different, and definitely the mass density around tracers is also going to be different. So we are going to look at two different measurements that we tried to do with this to actually find this some signatures of these different chameleon, different screening mechanisms, right? One is the marked correlation functions that involve the density, the local density of the galaxies and the whole solar masses. And then I'm going to talk about the weak lensing profiles around voids. So for the first case, this is work done by Joaquín Armijo, who is one of our students in Católica. He's moving to Durham now. Is to look at these galaxies that have the same clustering, these different simulations, right? In particular, F of R, and see what is the distribution of densities as a function, the distribution function of densities around these galaxies. And there are differences in the low density part, right? F5 in particular has a larger abundance of low densities around their galaxies, on the galaxies of this model. That's nice, because if we make a mark for the mark correlation that outweighs the low density regions, we should see the differences, right? So that's a good plan. And the other thing that is quite interesting is here on the right. This is the distribution of masses of the halos where the galaxies in our samples inhabit, okay? And what we see is that we have some mass, some average mass for GR, and if you move towards F6 and F5, the density increasing, the mass of the hosts increases. So this is another thing that we could use to do the marks, right? So this mark correlation is basically telling you what is the average value of the mark as a function of separation between galaxies. And that is what Joaquin basically measured. Here's a mark as a function of radius. This radius in megaparsecs, up to 50 megaparsecs. Different colors are different models. Dashed is for redshift, the dashed and solids are for different powers of the mark. Here's the expression for the mark as a function of separation from of the pair. And in particular, the result that we have here, we use the density as a mark. So it doesn't matter if we do a positive power of the mark or a negative power of the mark. Well, the differences between GR, which is the black line here, 1, and F5 and F6 are actually, lie well within the error bars. So there's not really, it's a bit unfortunate. We thought this was going to be a test that we could do, right? But the problem is that the density that we're using is the density that you obtain from the distribution of galaxies. So we're not using the mass itself. We know that the differences are in the mass, because with the correlation function being the same, it is actually also making the densities be similar. So the distribution of densities was slightly different, but for the less abundant galaxies. So it's not enough to actually see something in this particular statistic. That is something that one can actually go and measure with catalogs, right? So the other thing that we could do was to use as a mark the mass of the halo where those galaxies live. Now this may seem a little bit unpractical, because you can think, well, we have the stellar mass, right? But we don't have the halo mass. So the idea here is to try different things. So first, if you look down here at the relative difference in the marks between GR and F5, which is the green curve, you see that the differences are significant in different ranges of separation, but in all the panels, right? So what we're doing here is different things. So in the first panel on the left is we use a host mass with 0.1 dex scatter. We increase the scatter for the second panel, and then we start to do a sort of simple simulation of what would be a stacking of weak lensing in bins of galaxy stellar mass. And we still see the signal, right? And if we add an error of 0.2 dex to the weak lensing mass that you estimate for your bins, you still find the difference between the two models. So this is actually something that's quite interesting, particularly because the feasibility of this is actually larger to the right. You can actually go and measure this with catalogs today, right? If you can do the stacking of weak lensing mass estimates of different ranges of galaxy stellar mass to have different marks for pairs of galaxies, okay? Very good. So marks, yes. With weak lensing, there's something that we can use there, okay? Right, so but what about the lensing profile around voids? So to look at this, there's been a lot of literature about this, right? Different groups are trying to see what can be done with the voids. Voids are low density regions. The fifth force is unscreened there, so we can see their effects there, the effect of this force. So what we did is, instead of just using one void finder, we use 7 different finders. 4 that basically look for voids in 3 dimensions, in the full 3-dimensional distribution of galaxies in the simulation. And then we also use some 2-dimensional void finders, thinking in, for example, DAS or LSST that's not going to have redshifts, okay? So, as you can see, the different void finders find different voids, right? The spherical one sort of finds like spherical, like the largest spherical regions that are underdense at 20% the average density of the universe in galaxies, right? The watershed void finders basically fills up basins of low density with sort of like water, right? Until it sort of spills to the rest of the simulation. So it defines this very nicely shaped voids that actually the contours follow the filaments, right? And the Sobov finder by McNearing is also similar to the watershed. It also finds voids with interesting shapes. And these finds are the ones that we use in the 2 papers that we've done so far. And here's the detail. So the spherical void finder, watershed, Sobov, and we also use watershed walls. So instead of centering ourselves on the center of the void, we center ourselves on the walls and see what the density profile is to one side or the other in this case. And we use different 2D finders. To our knowledge, like the first 2D void finder was proposed by Gren and basically the DES collaboration in 2016 for the science verification data, which is fixed radius. On the sky, it can have 2 galaxies within it and nothing else. So this is basically underdense regions of in the skies with a fixed radius, right? And it basically detects this underdensities in projection. Yeah, that's actually quite powerful because if you think about it, there's nothing in the whole cone of that region in the sky. There's only 2 galaxies, right? So it's very underdense. And then we propose two different additional 2D finders. One is a spherical 2D void finder, which is just spherical underdensities, the largest ones that satisfy a given underdensity in projection, and also the 2D tunnels, which are just regional galaxies. So these are definitely tunnels. There's nothing in it all the way to the end of the survey, down to the flux limit that you're adopting. Okay? Very good. So here's the example of what are these different void finders actually finding, right? So you have the 3D void that you can find with Watershed that basically follows all the contours of the different filaments. The galaxies are actually the things that you use to detect the voids, right? So the galaxies are shown here as these red points. So yeah, we could have red points inside the voids. We said that, right? But in particular, a tunnel will actually have nothing within it, right? So this is like a good representation. The tunnel can actually go through several 3D voids as it goes through the volume of the survey, okay? Very good. So what are the results? Well, again, a little recap. We said that in voids, the fifth force points outwards, so voids should be emptier. Good. So we actually did this early on, 2015, measured the abundance of voids in FFR simulations with 4, 5, and F6. We did find that in the mass, voids tend to be larger when you use FFR. Okay, fair enough, expected, everything's fine, right? But what happens when you do this in the simulations that have the same space density and clustering for all the different models? There's absolutely no difference. So there's no difference in the size of the void because you're basically getting rid of the difference in bias of the traces that you're using, right? I mean, the difference is sigma 8. So sigma 8 is the same. The sizes of the voids are basically, if you find the voids with galaxies, are not going to tell you anything about any type of screening that you have, even though you're searching for voids, right? So there's no additional information in the sizes of voids to what you have in the 2-point correlation function, in a sense, right? Okay, that's a bit disappointing, but there are other things that one can do. One can actually do, for example, the velocity profiles in different directions, radial, tangential, the full 3D velocity. As a function of separation, just concentrate here on the black lines, which are basically the radial velocity, which is the one that would enter, I don't know, like in a simple way into redshift space distortion. So all component center, but just to see the differences, right? And so solid lines is the radial velocity. Colors are black for GR and the other ones for FFR. And what you see is that, yes, there is an increase in the radial velocity of galaxies around voids that are found using galaxies, okay? So this is great because even though we have the same clustering, 3D clustering, which is basically saying the same, we have the same projected clustering, which is something that one can measure quite accurately with surveys, we would still have a different redshift space distortion in this case. We did check what happens in a simulation with baryons. The effect is very small, so this is something that one can definitely do. But we don't have redshifts in LSST, and this is an LSST workshop, right? Thinking about LSST. One could do this with DESI though, right? So what other thing we can do, if not redshift space distortions, we can look at, for example, density profiles. So what is shown here are the density profiles traced by galaxies. So voids are found using galaxies, and we measure the number density of galaxies as a function of the distance to the center of the void. And again, everything lies within the error bars because the clustering is exactly the same. So the 2-point correlation function tells you all you need to know about the density profiles of voids, of galaxies, around voids, and the abundance of voids found with galaxies. Okay. But you can do this with the mass, right? So if you look at what is the density of mass as a function of distance from the center of voids that you found with these galaxies that have the same clustering, you do find differences in this case, right? And yeah, the differences are rather small, but they are definitely outside the error bars that you find, in particular for this volume, which is a 3 gigaparsec simulation. Later on, I'm going to show you the exact result that we expect for LSST of significance of these differences that we have here. Okay, So yeah, definitely, when you look at the matter, voids are emptier in FOFR, right? Because then the voids are actually being influenced more by the fifth force pointing outwards. So that's what should happen, right? That's what we find. And the results are similar for NDGP. So this is the same, or consistent between the two different types of screening, okay? And if you have this difference in the mass sensitivity profiles, you can say, well, let's look at what are the weak lensing profiles, right? And we did this initially for FOFR, and what we found was that this is something that goes with the tangential shear profile here, the differential projected density around voids, is that there is a significant difference, in particular for F5, between the signal for the tangential shear profile that you expect from FOFR and GR. So this is something that one can actually do, right? So lensing can be used to detect FOFR with LSST or DESI, right? And what we find is that this is especially true for the 2D finders. This is basically shown here. This is the actual signal to noise for an LSST type survey. What this means is that we've taken into account the volume that LSST is going to sample, and we also took into account the shape noise for the measurement of the weak lensing signal. So this is an actual signal to noise that one would expect to be able to measure for LSST. And what we see here is, here in green, we have the best signal that we find for a 3D void finder, which is a little bit impractical with LSST because we won't have redshifts. And it can find something that reaches roughly a signal to noise of 1, depending on what you do with the volume. You can make it larger to see what is the effect of a larger survey, or variations in the design and so on. But the void finders that actually find signal to noise larger than 1 are all the spherical versions, right? Are the troughs, the tunnels, and the 2D spherical void finder. The troughs reach roughly a signal to noise of 1 or 2. And in particular, the tunnels are the best that reach a signal to noise of about 10. So this is actually quite promising, quite interesting, right? And this is the result for FOFR. What happens when, we move to the Weinstein screening. So this work in particular was done by Enrique Paijas, who is a student at Católica at present. And so this is the work where we actually not just analyze FOFR, but try to find differences that can tell apart the different type of screening that you have in the two simulations. So this is comparing NDGP and FOFR. This is a SHED2 paper. So in this case, there are different things you can do with simulation, right? You can actually look at the profiles of the fifth force as a function of distance from halos and voids. So it's really nice. You know everything that's going on in there, right? But we try to see what happens with things that one can actually observe. So in particular, what you can do is to look at what is the mass function of the galaxies that are exactly on the borders of the tunnels. Because that is a place where there are going to be differences between the chameleon and the Weinstein screening types. And what we find is that with FOFR, the masses of the hosts of the galaxies that are in the borders of the tunnels are larger than GR, right, which is shown here in black. This is just a PDF of mass. And that doesn't happen for NDGP, right? It doesn't happen for the Weinstein screening. And why is this, right? And the only reason is that the fifth force doesn't reach the halos themselves, at least at the borders of these tunnels. So this is something that is going to look very different between NDGP, the chameleon, Weinstein screening, and the chameleon screening, right? And when you look at the difference in the signal to noise that you get by comparing these modified gravity simulations to GR, you see that the differences are actually quite extreme, right? FOFR lies here, right? This is the difference in the differential projected density around these 2D voids. In particular, this is for troughs, this is for tunnels. These are the typical errors so that you can work out the sort of signal to noise And this is shown here for the spherical body finder. The spherical body finder just has too large errors to actually be able to tell much about anything. So we need to stick here with the 2D case, right? And what you see that independent of whether you look at tunnels, troughs, or spherical 2D, what you will find is that the departure of the Weinstein type and chameleon type screenings is completely different. So there's something that you can actually use just looking at the weak lensing signal of two different types of 2D voids to work out whether one or the other screening mechanism is present, right? So this is actually quite interesting because we can tell apart these two different screenings by looking at the weak lensing signal around two different types of 2D voids, right? Not even comparing to GR, which is actually quite nice. Right? 5. Good. Okay, so chameleon is farther away than Weinstein for these 2D voids. So that's the main point. And actually, these are my conclusions already. So what we've looked at today is, okay, so we actually concentrated on simulations of modified gravity. But the objective of this is to actually look at different screening mechanisms, right? It's not really that, this is FFR and this is NDGP. It is more than we have chameleon type screening and Weinstein screening and GR, right? And what difference we can find between these different models, these different types of screening mechanisms. So that's what this is about, really, okay? So NDGP has a cosmological constant in it, but it has a screening mechanism for a fifth force. That's what we care about, okay? And when we do this, we have simulations, we have the same initial conditions, we have different sigma-8s for the mass, but we can actually take advantage of our lack of exact knowledge of how galaxies populate halos to actually make the populations of galaxies have exactly the same clustering in the different simulations. And this is great, right? Because all these simulations fit perfectly well Sloan, like the CMAS, EVOS, and everything, DES, etc., right? So in that sense, this is like a very, very nice tool to actually go and start playing and try to find what you can actually see in differences between these different models, right? So that's like a machine to detect different screening types. So that's really nice, okay? And that's basically what is shown here, right? That we have the same correlation functions at different redshifts and everything consistent with CMAS and so on, right? Right. Then we learned that when you do that, when you have the same 2-point correlation functions, then same 2-point correlation functions and same space density of galaxies, then if you look at the abundance of voids, you won't see any differences. And if you look at the density profile of galaxies around voids, there's also not going to be any differences. What you need to do is somehow to look at the mass distribution around those galaxies or those voids. So we marked correlation functions. We actually managed to see a difference if we use weak lensing to detect the mass of the hosts of the galaxies that we're using to do the marked correlations, okay? Of course, redshift phase distortions can also be used to actually find differences, for example, with DESI. And weak lensing can actually be used not only to detect the departures from GR, but also to try to see if either, if one or other mechanism for a screening is present or not. I'm going to stop here. Thank you very much.
Yeah, so any questions for the next one?
So the plot you showed for the change in the void profiles in FFR gravity, that's an important issue, right? We don't know outside of simulations how to, what should I say? We know that the void profiles should be different in modified gravity, right? And at the moment, the only way to find that is by, as you've done, doing a simulation. Is it possible? Have you tried to kind of fit some formula to that, so that we could have a prescription for the relation between fifth forces and changes to void profiles without running a simulation that could then be used, in non-simulation work?
No, we haven't done that, really. It's really difficult. So that would be possible, right? But the problem is that these are, so we're using 3 different 3D void finders where we don't expect to find actual measurable differences, at least for LSST. Okay. So we should do it with the 2D voids, right?
So what do you mean you don't expect to find measurable differences?
So the weak lensing differences that we predict for LSST and DESI are below a signal to noise of 1. So it's within the errors, the difference that we expect for the 2 surveys, right? So I don't know Euclid. We haven't done Euclid, right? But for the 2D voids, one can actually think about doing the density profiles of the mass, but they would look different for the 3 different void finders. So since we have so many different void finders, we didn't really go into trying to fit the actual shape, right? But one thing that you could try to do is to work out the real space profile of the galaxies around those voids and try to predict the weak lensing signal from that and see, for example, what would the expected model for the weak lensing is. But but you're right, we will need to parameterize that. So we haven't thought about even doing that yet. So, but it's actually interesting. But I think it's so, it varies so much with what you do to find the voids.
Really?
It depends. I mean, it's like if you design your void finder, you should do the formula yourself. We can actually do it for free. Yeah.
All right, thanks.
Yeah, thanks.
More questions?
So I have 2 quick questions. So the first part of your talk, you mentioned the spherical collapse model, and then you talk about simulation. So how the spherical collapse model, do you know how good the spherical collapse model is compared to simulations? That's one question.
Yes.
And the other question is I don't understand why there's no difference in the 2-point correlation functions.
Okay.
Because you're looking at empty space, and there's no screening, and that's where you would expect some differences.
Yes. So for the first part, right, the spherical solutions are really informative, right? They sort of let you have an idea of where you expect to find this 5th force and what effect it should have, right? And then you run simulations, and when you look at the mass, you see that you have an enhancement of the mass of halos due to the 5th force pointing toward the halos, and you have larger voids in the mass. Okay, so you say, okay, so voids are emptier, right? Perfect. So it is informative in that way, but one thing that it doesn't take into account is biasing. So, and one of the surprises is, yes, you actually see that the voids are emptier in FOFR and NDGP, emptier of mass, right? But when you actually put galaxies in, if you put them carefully enough, you find no differences, right? But the reason for that is, maybe we can, it's just the bias, okay? So the density profile in mass, so let's say let's put here delta, right? So
the bias depends on the gravity, on modified gravity also?
It will also depend on that. So say that you have a density profile like this for the mass, right? Mass. And then if you have a bias that's larger than 1 for your galaxies, and you put that, like this, then you have to increase the delta, right? So it is going to be something like this for your galaxies. And if you use something like this threshold, right, for defining a void, you won't find it in the mass, but then you will find it in the galaxies. So you can actually change completely the number of voids that we will find as a function of radius if you just change the bias of your tracers. Yeah, and it basically makes it all go away, all the difference that you see in the mass. But weak lensing can still be useful there, right?
And the correlation, the 2-point correlation function, why is it the same?
Right, the 2-point correlation functions are made to be the same for the galaxies.
But it's made to be the same.
On purpose. So with the halo occupation distribution, you basically put different numbers of galaxies for a halo of a given mass for the different gravity models, right? And in particular, if you have a higher sigma 8 for FOFR, you just populate halos of slightly lower masses in in FOFR to basically weight more halos of lower mass that have lower bias factors, right? Numerically lower bias factors. So the amplitude of the correlation function goes down. And it basically cancels out that excess of sigma 8 that you have on the mass. And that way you have the same correlation function. So the one halo term is a bit more complicated, but our HOD modeling is very simple. You can actually make the correlation function be exactly the same from very tiny scales to very large separations. It's possible to do that. But it's made by hand, right? Yeah. So it's this way you have the same galaxies, right? Same initial condition CMB, but different gravity, different distribution of mass.
More questions? So I have a naive question.
Okay.
So do these simulations include baryons?
No.
And would including baryons help with breaking this degeneracy between bias and somehow?
Right. So yeah. So it is not. So the dependence of the bias as a function of halo mass is going to be slightly different in the modified gravity models because of the fifth force. The way in which gas is going to settle down within halos is also going to be different because equilibrium is going to be reached in different stage of the halo, right? So the galaxy population is not the same. But we did look at what happens in simulations with baryons in GR, and the effect of baryons don't vary too much the statistics of voids in particular, right? The density profiles of mass, it doesn't change it that much. Baryons are rather important in small halos, and not so much on these very large scale structures. Voids are tens of megaparsecs in size. And even the velocity field changes, but only by a little bit. So it's a minor effect. And right, if we did have hydro simulations, then we wouldn't be able to put galaxies by hand, right? So that would be an interesting exercise to see if we can actually manage to select samples with the same clustering in actual hydro simulations, but that's ages away, right? It's really difficult to do hydro with clustering. The volume needs to be too large.
More questions?
So for testing cosmologies, why do you think using voids is more effective than other kind of tests?
Right, so I've shown two different tests, right? One that is a marked correlation function that weighs the masses of the halos where the galaxies live, which was a little bit unexpected, right? I mean, for that to work, because the initial motivation was the fifth force acts on low density regions. And people thought, oh, voids, let's do voids. So that was like the initial motivation, right? But in the end, it turns out that you can use voids. But for example, what you actually need to think about for tests in general is how to find what is the mass around any type of object I find using tracers. Because that is where the difference is. There is a difference in the voids, but there's also a difference in the host halo masses of galaxies. So the two things end up being like plausible ways to find differences. Well, in particular, the voids allow us to find what the effect or what the details of the screening mechanism would be, which is really, really nice.
Are there any more questions? If not, let's thank Nelson again. So there's a coffee break, and we come back at 11.
That's